For this particular video, we are going to look at the electrophilic aromatic substitution reactions. And to figure out, based on your substituents on a benzene ring, whether they are going to act as a activating or deactivating groups. We will have to understand what does these two terms mean for us. We can memorize this table, but a better way would be to understand how these groups are working. And you will need to remember your resonances, the 5 ways, the 5 patterns of your resonance. To begin with, let's just think that we have our benzene ring with a group on it and assume that this group G is activating. What does the term activating mean? A benzene ring is your nucleophile. It is the electron-rich species. If the group that is attached on this can pump electrons into the ring, making this ring even more electron-rich, we say that group is activating. If it is pulling electrons away, then we say it is deactivating. So let's assume that this G is activating. We have our reagent and we also have our catalyst. And this is overall reaction that is going on in the electrophilic addition reaction when a substituent is already placed in the ring. So for the incoming second electrophile, where will this incoming electrophile go? It can go on the 1, 2 location. It can go on 1, 3 location. It can go on 1, 4 location. So remember, 1, 2 locations can be either 1, 3 locations can be either when your group is activating, there is a sigma bond between the group and the benzene ring. This benzene ring is your nucleophilic part, and the incoming electrophile will be some form. It can either be bromium ion, it can be the neutral sulfoxide molecule. So you will have to be a little careful about your incoming electrophiles. The incoming electrophile and this G, how is it going to attack? Your sigma bond between the already existing group and the benzene ring can show some input. So alkyl groups, for example, are all electron donating group. They have a plus I effect, all of the alkyl groups. But the benzene ring on its own has some resonance. Let's assume that our incoming electrophile is on the 4th location, just like here shown by the bromium ion. If this is the case, how many resonance structures can I see? 1, 2, 3. Okay. And so having this particular intermediate is possible for me. On the other hand, if my activating group has a lone pair on it, not just a pi, but also a lone pair on it, my resonance hybrids will have additional hybrid structures. It will have at least 4 resonance hybrid structures. Having this lone pair will give this intermediate carbocation. Because of this plus charge, I have a carbocation, additional stability. And this stability will make your final product easier to form. When it will be easier to form, this reaction will go comparatively faster. So we are going to learn about comparative terms, not just by itself, but these are going to be comparative. You need to know how to draw these intermediate carbocations, how to move around the arrows, and if you have lone pairs present on your existing group G, how to give electrons to that system. So here you just have sigma bonds, sigma electrons getting in the ring. But in here, you have the sigma and the lone pairs. So you have 2 effects going on. Still, other resonance structures will occur. So the donating effects of your existing group can be inductive through the sigma bond or through resonance because of the presence of the lone pair. These are the 2 types of donating effects that your existing group can give. If we try to understand this better, we will have to look at the overall mechanism. Looking at this mechanism, what is happening here? You had an aromatic system, and now you do not have an aromaticity anymore. This is a very stable system. The aromatic system is quite stable. Why would it want to go ahead and destroy its stability? There has to be a prompt enough for the reaction to occur. So there are basically 2 steps in your electrophilic aromatic reactions. The first is the formation of a delocalized cation. The formation of this delocalized cation is dependent on how stable this cation would be. Do you get 3 resonance structures or do you get 4 resonance structures? Getting 4 resonance structures will make this delocalized cation faster. But having only 3 will make it slower compared to this reaction, whatever made the 4 resonance structures to occur. We just saw it here, how these delocalized carbocations will be generated. So the reason this aromaticity is destroyed is that the resulting delocalized cation will be stabilized by the electron donating group. What are the 2 donation methods? The sigma and or the resonance. The second step is the faster step. Why? Because now the aromaticity is being regained. One of the hydrogens is being abstracted out by the existing base in the system. So if you remember overall, what does your 2 steps are? how this delocalized cation can be stabilized, you can know which of your reactions will go faster and which of your groups will go slower. Let's look at one example also. Let's see that you have a C single bond C. Whenever you will have the single bonds, the first bond that forms is the sigma bond. When you have two atoms, the first bond that forms is the sigma bond. The second bond between the same two atoms, when it forms, makes the pi bond. Looking at these four structures, let's look at who is going to be more activating, who is going to have the reaction faster. And these are our G groups, the groups that we had labeled as G in the earlier page. So if I look at H has nothing to donate. There is no sigma bond, it's a non-polar group. And so the donation from the H is only via the inductive effect. However, having this CH3 will give you a little bit more electrons than just having hydrogens. Why? Because carbon has more number of electrons on it as compared to hydrogen. So the sigma bond, induction only. But if we look at O and if we look at N, both of them have lone pairs on them. And so these lone pairs can also be donated to the ring. So what are the effects that we see? Let's look only at our aniline, where an amine is on the benzene ring. So beside the sigma inductive effect, we are also seeing the pi resonance. So clearly between A, B, and C, the aniline's amine is giving more electrons to the ring, making this ring more nucleophilic. Between A and B, it is this ethyl group which is making this benzene ring more nucleophilic. So we are comparing between A, B, and C. Who can give more to our electrons? If we look at our oxygen's effect, similar sigma and pi donations are possible. But if you have to compare between this carbon, is between C and D, who is going to be better at accommodating or giving more electrons? This is the time that you have to remember your electronegativity. If you look at this resonance hybrid in this case, and if you look at this resonance hybrid in case C, your electronegative element has a positive charge. Between oxygen and nitrogen, oxygen is more electronegative and hence will not like the positive charge on it. So between D and C, nitrogen will be able to accommodate this positive charge better on it. Hence, this cation will be more stable than this cation. The aniline's cation will form first, then phenol's cation will form. Because this forms first, the overall reaction will go first. This forms second, the overall reaction will go on later or slower than just aniline. So knowing this, there are a few other things that you must know about the rate of reactions. At room temperature, at the standard room temperature, the rate of reaction is whatever that number is. At every increase of 10 degrees, your rate of reaction will double. So for every 10-degree increase in temperature, the rate of the reaction will double. The time of the reaction will also become less. So when you increase temperature, rate of reaction increases, but the time of reaction reduces or decreases. So this is also something that we are going to look at experimentally in our class. To summarize, how can you figure out what kind of a group that is attached can be activating or deactivating? First, it should have lone pairs on it, but just having lone pairs is not enough. So let's start at activating groups, and we are only going to look at the atom which is directly attached to the benzene ring. So if you look at the benzene ring right here, what is the atom which is directly attached? This oxygen is directly attached. This atom which is directly attached should be able to donate its electrons to the pi system of the ring. Can it do that? Yes, it is able to do that. But if you look at this particular system, this also has lone pairs. But will this atom be able to donate its electrons to this bond? It will be very difficult. Why? Because it has two oxygens on it, and the electrons from this nitrogen are being pulled in all the directions, to this oxygen, and only few lone pair electrons are left from this oxygen to go to the benzene ring. So this nitrogen is not able to donate its electrons to the ring. The second thing is, when you form the carbocation, the atom which is directly attached to the benzene ring should have a positive charge on it as a carbocation. So once this carbocation forms, oxygen has a positive charge on it, the double bond. Now, this is something that might be a little tricky for you to see here. If the atom which is directly attached to the ring is already positive, okay, it is not in its carbocation form, it is a positive in its neutral form, then it will be a deactivating group. Why is this carbon a positive, a partial positive? Because these fluorines are pulling electrons away from it, making this carbon partially positive. So these two things are a little tricky, but try to understand. This is in its carbocation form. This is in its neutral form. You want a positive charge on the atom which is directly attached to the benzene ring as a positive here, but not when it is in its neutral form. And the third thing that you must remember is the deactivating groups. First, of course, in its neutral form, the atom directly attached must not have a positive charge on it. If it is already positively charged because of other atoms or any other conditions, it will become a deactivating group. A second thing that makes the groups deactivating are when they have a double bond or a triple bond on the atom directly attached to the benzene ring. When you have that system, you will always have deactivation. The reactions of these molecules will be much slower than the reactions of those which have activating groups on them. So what are the overall factors that influence our rate in electrophilic addition reaction? You need to increase the nucleophilicity of benzene ring, the electron richness of the benzene ring, so that it can attack the electrophile. So this is your nucleophile. The benzene ring will be the nucleophile, and it needs to attack the electrophile. The stabilization of the delocalized carbocation is also very important. The faster this forms, the faster our step 1 will occur. Okay. And the third is, if you provide heat, your reaction rate will increase. How much will it increase? For every 10-degree rise in temperature, the reaction rate will double. That's how fast the reactions become. So once you have finished the 3 parts of your experiment, we will need to fill in the data sheet. Make sure when you're showing me the data sheet answers, you have to describe chemically and in sentences. So when I say chemically, I need to see both your structures in their carbocation form. And then I need you to tell me what are the donation methods by each of those groups. And then who will be the stronger activator among them.